Um, I'd like to thank you all for staying, and I promise I won't take much of your time so we can enjoy ourselves at the happy hour. I'd like to start with a question. Imagine a rich man offered you $10 million just so you could find his needle in his haystack. Of course, we all would be tempted, but it wouldn't be very smart of us if we didn't make sure there actually was a needle in his haystack. Well, looking for life in other planets is a similar task, so it's important we understand where life cannot be found.
Hi, my name is Arthur. I'm a computer developer, and I have a thing for astronomy since ever. I work at USE, the first insurtech of the country. It was born as a startup to change the insurance market in Brazil. By the way, we are hiring, so if you want to work with Ruby on Rails or iOS development, Android development, Guidewire, Java, talk to me later. And he is Lucas, probably the youngest speaker at the Conf ever. Uh, he took his crush on astronomy to another level. He's a student of astronomy and physics at the University of São Paulo, and he's currently working with the structure and the dynamics of the galactical spiral arms through the study of open clusters. Not computer clusters, just star clusters. What we brought here today is a glimpse into his scientific initiation project. We may not have all the answers. I certainly don't have them. But if you want to contact us, feel free to write to us through our Twitter accounts. When we try to understand the universe, we inevitably stumble across a question that's really hard to answer. Who are we? For many centuries, we put a lot of importance on humankind, but at the end, we are just little grains of sand in a tiny little planet in the corner of one of so many galaxies. Even the universe may not be unique. We don't know that for sure. So we are basically unimportant. Well, there is this lesson on public speaking that says we should build the audience's morale. We are not doing it right. But our point here is that we are a living miracle. Our existence is statistically impossible, and there is no evidence that there is anything slightly like us out there. Nonetheless, we are putting all our efforts to find it. And this is the purpose of this project. Let's find other grains of sand. But what are we looking for exactly? First, there is the needle, and the needle is developed life. We are talking of intelligent life, of sentient beings that are capable of communicating back. We get asked a lot, why do we search for life that resembles us? For example, why do we look for water? Maybe life out there does not need water to develop, right? That's a fair question. So, what if life out there is immune to our senses and invisible to all our equipments? Well, it may be the case, but honestly, what's the difference for us from such a life and a life that does not exist? On the other hand, we have the haystack, and the haystack is our galaxy, the Milky Way. It is a haystack because it's huge. It has a little bit more than 100,000 light years of distance from one end to the other. And that means that a light beam traveling at light speed would take 100,000 years to get across it. Our estimate is that it contains 250 billion stars, given or taken extra 150. It's a huge number. If you are a bit optimistic and take a guess like 400 billion stars, we are talking roughly of 10 stars for each grain of sand on Earth according to some estimates. If we Google where we are in the galaxy, we are probably going to find an image mostly like this, with a yellow dot somewhere saying you are here. And looking at this image, we have the impression that we are closely surrounded by stars, but that is deceiving. The closest star from our sun is Proxima Centauri, and it is more than 4 light years away from us. So the stars are really far away from one another.
With this number of stars, it gives us hundreds of billions of planets that can host life. So, can we narrow down our search? Well, first, we need to understand the conditions that make the existence of life as we know it possible. And these are the conditions you might have already heard of. The first thing we need is what we call a stable source of energy, like our sun is to Earth. It's better if it's not a very wild star with insane variations in brightness and a lot of plasma ejections from the star. And it needs to be stable because we need the distance from the star to what we call the habitable zone to be constant. The habitable zone is where water can be easily found in the liquid state. If it's closer than that, it's going to be too hot and water is going to evaporate. And if it's too far, water is going to be found as ice. And as you might already be thinking, the other thing we need is water. We all know the importance of liquid water for life here on Earth, but we might not think about the importance of water vapor. Water vapor is a key compound of the greenhouse effect. And remember, the greenhouse effect is a natural process that warms the surface of a planet and allows the temperature to be constant even during the night. The other thing we need is what we call a benign environment. These are things like a rocky planet so we can hold water, and the existence of a magnetic field so we can protect the planet from plasma ejections from the star, and things like an appropriate composition of the atmosphere, and so on. But there are also the more complex conditions for life. These are the ones that make finding developed life a little more unlikely. It turns out that the greenhouse effect produced by water vapor is not that stable. If it gets too hot or too cold, it's hard to come back to the temperature it was. So we need what we call a continuous geological activity on the planet. These are things like volcanoes and erosions, things that emit and absorb gases, maintaining an equilibrium. The other thing is very intuitive. We need a star that lasts longer than the time required for life to develop. So Earth is about 4.5 billion years old. So it's natural we look for stars that have at least that age. So very young stars are out of the game. And the next thing is not very mentioned, but it will be the one we'll be talking on this talk today, which is the distance from the galactic arms. But first, let's clarify a couple of things. What are the arms? What's going on in there? Well, we live on a spiral galaxy, and this is an illustration of a spiral galaxy. It's a disk that has these patterns that we call the arms. And you can think of the arms as waves propagating on the disk, and we can compare it to a traffic jam. But it's just a region of higher density, but the cars, in this case the stars, that make up the traffic jam are not always the same, they're always being replaced. But the difference in density is not that expressive. So how come we see those regions so highlighted from far away? Well, the the gas that's on the galaxy, it suffers from the gravitational disturbances created in the arms, and it collapses, forming new stars. And it turns out that the brightest stars are the more massive stars. And also, the bigger the star is, the less it will live. That's because a bigger star needs way more fuel to counteract its gravitational weight than a smaller star. And that's the reason why we see those regions so highlighted, so distinguished. It's because it's a region of star formation, there are a lot of bright stars, and those bright stars don't have time to leave the arms before they die. And that leads us to the danger that spiral arms offer, and that is the death of a high mass star. The death of a high mass star is a very energetic phenomenon. When a high mass star comes to the end of its life, all the elements that make up the star fuse into each other, making other elements heavier and releasing a huge amount of radiation. and that's what we call a supernova. The appearance of a supernova nearby could entirely destroy our ozone layer and ionize atoms in our atmosphere, forming harmful compounds, and could also harm phytoplanktons and reefs, destabilizing our entire ecosystem. And not to mention the gravitational impact it could produce, taking Earth away from our comfortable orbit. So, if you want to find life, we better start with a star that hasn't crossed an arm in a long, long time. But is that even possible? Well, what is observed is that the arms and the stars orbit the galaxy in a different manner. The arms are represented by this dashed line, and it orbits around the galaxy like a solid body. It's not a solid body, but it orbits like one. That means that the further it is from the center, the fastest it travels. On the other hand, the stars, which is represented by this full line here with the dots, it is approximately constant. It has a speed approximately constant for every distance from the galactic center. And what we can see is that there is this region right here where those two velocities are the same. If we have a star that is in this region, it travels with the same speed as the arms. They orbit together, and that's what we call co-rotation. If we have a star that is in co-rotation, which is this radius here, and it already has a distance from the galactic arm, it's going to keep that distance constant because they have the same speed. They're going together, never meeting each other. On the other hand, if we have a star that is closer to the center, it's going to have a greater velocity than the arms, and it's going to travel faster than the arms. In this case, that the star is traveling faster than the arms, the star would cross an arm, which is a very dangerous place. And the other case would be a star that is further from the center, in this case right here. In this case, they have a velocity that's small than the one of the arms. So in this case, it will not cross an arm, but it will be crossed by an arm, which is equally dangerous. So if you want to find some kind of developed life, we better start with this safe region that is the co-rotation.
We are talking of finding life out there, but how can we actually do it? We are going to see some super helpful tools, but let's start right away with the most polemical choice. Guess what it is? You're right, the programming language. We chose Python. Why?
Um,
Here comes a wake-up call for all developers out there. We tend to choose the programming language based on the language we are more acquainted with. Then we come up with rationalizations, trying to convince ourselves that our decision was based on logical arguments. It's not exactly true. At the end of the day, it's not always the language we worship the most that gets the job done. So we have to be humble and honest and choose the right tool for the right job. We didn't choose Python because we are good at it. In fact, we know so little of Python that sometimes we felt like children groping the musty walls of a dark underground corridor. But if you know how to code, you can find your way through the uncertainties of a new language. Google is your friend. Stack Overflow is your dungeon master. Use them wisely. We chose Python because it has amazing scientific libraries like Matplotlib, SciPy, GalPy, and so many others. Then we had a huge problem to solve. We are talking of things that are light years away from us, things that can be hundreds of thousands of times bigger than Earth. While it may work well in the minds of the astronomers, for us, mere mortals, it's really hard to see what's going on. So we needed to find a tool that allowed us to have a visual representation of the work in progress. And for that, we chose Jupyter Notebooks. It has a neat web interface that allows us to write text that will later on work as a documentation. But we can also write Python code in there and have the result nearly in real time. We are going to see it in action in a moment. And last but not least, most scientific research is built on top of a huge data set. We need data. We are talking of checking the stars to know which one has a good chance of having planets with developed life as we know it. So first, we need to know the stars, right? Luckily for us, we don't have to do all the work ourselves. People a lot smarter than us, with so much more research, have already done that. The ESA, the European Space Agency, is mapping the galaxy, and the result is Gaia Catalog, which is the foundation of our work. It's free, it's open, it's on the web for anyone who wants to use it. I think it's time to take a break from the slides and let's get our hands dirty a little bit. For those who does not know it, let me introduce you to Jupyter Notebooks. This notebook is in my GitHub, so you can go there later and read things in your own time. Feel free to make comments, open pull requests, and issues. If you are good at Python and know a better way of doing that, please let us know. I think the best approach here is to start by the end. So let's see the result of this notebook. You're looking at an animation of our galaxy, the Milky Way, spinning around with its arms. Our first impression is that it works like a disk where everything moves together, but that's not true. As Lucas said, the movement of the stars can be really chaotic. So we plotted those three stars, and bear in mind that they are completely out of scale, okay? They represent the three possible outcomes of the speed of a star in comparison with the speed of the arms of the galaxy. Look first at the blue star. Its movement is slower than the arms, so it will inevitably be crossed by the arm. And as he said, the arms are really dangerous places, so life that orbits that star is probably doomed. Then we have that red star. It has the opposite problem. It moves faster than the arms. It will not be crossed by an arm, but it will cross an arm. So its destiny is probably going to be the same. And finally, we have that purple star. It moves at the same speed that the arms. The animation is not 100% precise. It should not be touching the arms, but I think it's good enough to show our point. It's never going to cross or be crossed by an arm because it is in rotation. And, okay, never is a strong word, but it's very unlikely it's going to happen. And we want to be around that star because it's not in our agenda to be blown up by a supernova. Now that you are all hypnotized, I'm going to show you the best code of your life. The best code of your life. Uh, this works like a warm-up for what comes next. There are some key concepts here that are going to be useful to understand the next notebook where we are going to integrate the orbit of the star. So we start with this matplotlib inline here. We are just telling Jupyter to plot charts here in the notebook. Then we imported a few libraries, like the gist of it is we are importing pyplot and animation from matplotlib, and the image from scipy, then numpy and image.io. It's better, I guess. So we start by reading this image, the galaxy white, into this img variable. This is the image of the galaxy we're seeing right now. It is in the semi folder of this notebook. Then we had to create a figure to hold the entire animation. We created the figure and configure it by setting its DPIs, its size in inches, and we also created an X and Y axis, a 20 by 20 axis. Then to draw the stars, we used circles. The circle accepts a few parameters. The first one is the X and Y position. It does not matter very much now. We are going to change it later, so never mind them. But then we have the radius of the star and the color. Let's skip the next two methods, because the next executable line of code is this call to the animate function. And it accepts a few parameters, like the figure to animate, the init method, the animate method, and other things like the number of frames, the interval between frames, and so on. You can read the full list in the documentation. Then we are just hiding the axis, saving the result in an MP4 file, and plotting something here. As you can see, Jupyter queued the animation and plotted the static image. Let's get back to the methods we skipped. First, we have the init method. There's nothing special about it. It's going to be called once before the animation starts. We are just adding the stars to the axis. But there is magic in the animate method. It's going to be called once for every frame in the animation. It's here that we are going to move the stars bit by bit, one movement for every frame. We have even the number of the frame passed through this method in this I parameter here. As you can see, we have 3 blocks of codes, each one for one different star. We are just moving the X and Y position of the stars. And as you can see here, all X and Y's starts as 10, 10. So 10, 10 is the center of the orbit of the stars. Then we have here 8 that's multiplying sine or cosine of something. We all know that sine and cosine varies from -1 to 1. So what we have here is 10 minus 8 to 10 plus 8. We can safely say that 8 is the radius of the orbit. And the same thing for the others. This one has 2.5 of radius, this one has 4. Why do we use sine or cosine? I know it's not very intuitive at first, especially if you don't work with this kind of things in your daily routine, but those mathematical functions force the movement of the stars to follow a circular path. If you want to know more about it, you can go to the GitHub later. I put a very cool animated GIF here that explains this process. This is really nice. We are even multiplying the I by different numbers. Here we have 0.5, here we have 2. We are just changing the speed of the movement. After moving the stars, all that's left is to rotate the galaxy. Our first attempt was to use an animated GIF. It didn't work because, as you saw down there, Jupyter queued the animation and we had a static image. So we decided to move the galaxy as we did with the stars. Then we tried to use an image with transparent background. It didn't work very well because it left a trail behind that we could not erase. So we added a white background. It worked better, but after every movement of the galaxy, we had the impression that the galaxy was shrinking because the image was being resized to fit the figure. So after struggling an entire hour with that, we went to the documentation and we found this reshape false here, and that worked like a charm. So here is an extra tip for today. Go first to the documentation. So thanks to that notebook, we can now see what we are trying to accomplish.
As we've seen, the Gaia catalog has already mapped around 1 billion stars, and that data is free, accessible for all those who want to use it. It's hard to imagine recent astronomy without a huge amount of data. And with that comes the need of using coding to process all the information. What we're seeing here is an extract of the Gaia catalog. But this catalog gives us things in the equatorial coordinate system, which is not very good for our purpose. It's good for when you're trying to locate things here on Earth, because it gives us things like the distance from the equator on the on the sky in angles. So we're using this other extract of the same Gaia catalog, but now in the galactic coordinate system, which is way better for our purpose.
Wow, this looks like hell. It's really hard to understand what is what looking at that. We can't even understand at first that those are columns. So if we go to the documentation provided by Gaia, we can learn what each column means. You know, here we have the columns. For example, the first 18 characters in each line. Let me show you what a line is. So this one is a line. It spans for 2 lines here because I increased the font size, but this is a line. So the first 18 characters go to the name of the object, then the next 8 to the longitude, and so on. We also have here this label column. That's because scientists used to use symbols to represent things. So those are the official symbols for every column. Um, Working manually with the catalog is not a good idea. Not only because it has too much data, but also because, as you can see here, we have some gaps, and these gaps are missing information. In order to integrate the orbit of a star, we have a set of rules that must be fulfilled. For example, we need to know the radial velocity of the star. It's impossible to do it otherwise. So instead of filtering data manually, we created a very simple Python crawler to do the hard work for us. There is nothing very special about the crawler, so I'm going to go through it very quickly. This crawler does only two things. It reads data from a source, and the source can be either the web or a file. We did that because we were not sure if we would have internet connection at the time of the presentation, or even if the catalog was going to be up and running. So we decided to accept both ways. So we read data from a source and we print the results. If we see the print results method, it looks to have lots of lines of code, but most of the lines are just formatting the result in a nicely beautiful way in the terminal. Let me show you it in action. As you can see, it already looks like a table. We are only printing the columns that are important and relevant for us, and there is no missing gaps anymore. So we are ready to pick any object here and work with that. The secret of the crawler is actually in the cluster class. I pasted the documentation here to make things simpler, and it has a class method called fromLine. This method receives one line of the catalog, and from it, it will instantiate a cluster and extract data according to the documentation. So you can see here that the first 18 characters goes to the name, the next 8 goes to the longitude, and so on, as I told you before. Then we created a method for every attribute using the scientific symbols, so anyone can use this project. And here at the bottom, we have a very nice valid method. It's here that we put all the rules in order to integrate an orbit. So for example, I told you that we need the radial velocity, and here I am saying that it must be present. So if we go back to the print results method, what we are doing here is really simple. We read the catalog line by line, we instantiate a cluster with data, and we check if it's valid. If it's valid, we print it to the terminal.
But as we can see here, the catalog only gives us the position and the velocity of the stars. Even if we already pick the stars that are already in rotation, how can we know that star has always traveled a safe path? Well, for that, we use Python to go back in time and analyze its behavior throughout its existence. And that's what we call an orbit integration. An orbit integration is just a simulation of the trajectory of a celestial body using its current parameters and knowing the physics that are applied in such context.
We have here another notebook. It's also in my GitHub, so you can go there later. And it's finally time to integrate the orbit of a star. And again, to integrate the orbit, it's to make the object goes back in time. We are finding its reverse trajectory from the current moment to its birth, so we can know if it has always been in rotation. It starts in the same way we started the other notebook with matplotlib inline here, and then we imported a few libraries, but this time we have a highlight. The life of the party here is Galpai. The first version of this project was done using IDL, which is another programming language, and we had hundreds of lines of code just to integrate the orbit. You're going to see that Galpai allows us to do that using one single command. So the first thing to do is to choose a potential to use. If you remember this chart that Lucas showed to you, we have here the speed of the arms of the galaxy in comparison with the distance from the center of the galaxy. It's linear, so we have this dashed line, but we also have here this line that represents the speed of the stars in comparison with the distance from the center. It gets very fast, very quickly, but then it stabilizes. And the potential is going to be used as a guide. It will represent the line of the stars. So we chose the logarithmic halo potential. There are many other potentials you can choose from. We put some examples here. You can read the full list in the documentation. But this one is the simplest one, and it worked better for us. Then it's time to pick an object from the catalog. We choose that one that has 10 billion years of existence. This is the amount of time we are going to go back in time. Then we created that TS variable. It works like an array. It starts at 0, it ends at 10, which is the age, and then we divided this interval in 1,000 small pieces whose units are in giga years. It works more or less like a timeline, just like the frames in the previous notebook. The animation is going to change the movement of the star bit by bit according to our timeline, which is this TS variable. And in order to integrate the orbit of a star, we need, well, an orbit. So we created two, one for an object that is in rotation and one that's not in rotation. The orbit has a few parameters. The most important one is this really weird VXVV. Don't ask me why it's called that.
This parameter is where the input from the catalog should be. It gives us the relative initial conditions, such like the radius or the radial velocity or the transverse velocity and so on. I say it's relative because we need to set what are the parameters for our sun. Here we're saying that our sun is 8 kiloparsec away from the galactic center and it has a velocity of 230 kilometers per second. So in this case, this orbit, this first one, has 95% of the radius and so on.
Now that we have the orbit, we are ready to let Galpai do its dark magic. So we call the integrate method over the orbit. We have the orbit calling the method, and it receives the TS variable, the potential, and then a method. I'm not going to dive into this method, but just for you to know, we are using this RKC6C, which stands for the Runge-Kutta method. To plot a chart is boring, so we animated things a little bit. So let's first see the orbit that is in rotation.
Oh.
Now let's see the orbit that's not in rotation, which is way cooler.
Oh. As we can see, the orbit that's not in rotation had a little variation in the radius. It went from, I don't know, 7.6 until almost 9.2, which is not a lot, and has certainly stayed in co-rotation. On the other hand, this other case had a huge variation in the radius. It went as close as 2.7 kiloparsecs from the center until almost 8 or 9 kiloparsecs from the center. It has certainly left the rotation region and has certainly had a speed greater than the one of the arms and has definitely crossed an arm. So this is a star that's probably not hosting developed life. So what are the consequences to what we've done? Well, this is an illustration of our galaxy, and this was the search area for life we had before. We wouldn't make any time for the happy hour if we had to check every single star in their region. But now, if we only choose those stars that aren't in rotation and far away from the arms, we're left with a much smaller area, which is very handy when you want things to be found before the world ends. But what about us? Are we doomed? Should we be worried about a galactic motivated mass extinction event? Well, no. This is where we live, in a very cozy spot of a banana shaped co-rotation region. So, despair not. We're safe, at least for now. Orbits are a very fragile thing, and we never know when something's going to happen that's going to change everything we observe. But that's a very unlikely event and won't happen anytime soon. So now we're a little bit closer to finding out if the predictions made by science fiction are somehow similar to what's out there. And if so, we hope that some are more friendly than some we know about.
Let's all pay attention to the next slide. That's all we had about global warming. Thank you very much.